we have a bare bones interactive proof system written in Jai. Not that that matters, but we're going to demo it and show you how it works. It doesn't have everything that you would expect a modern proof system to have. It's just a demo showing what's possible so far with a small system. So, for example, what we're going to try and prove is that we can expand a plus b times c plus d into this whole expression here on the right. And the reason you might want to do that is that technique becomes useful when you factor polynomials, and so it's just a good technique to know. And you'll notice that we have all these assumptions. So this is about what a, b, c, and d are, and then there's some facts here, and this is a minimal collection of facts that we can use to prove that this is true. And you might say, well, why are these on different lines? And as I mentioned, this is a demo. I will add a syntactic sugar to be able to say that a, b, c, d are in the real numbers, and of course here you see that the for alls are 1 by 1 as well. That can also be improved, but again, this is a demo, this isn't the final product. So what I'm going to try and do is I'm going to try and expand this guy, and the only rule we have is when we have 3 elements. And so what I'm going to do is that I'm going to start by showing that c plus d is a real number, which is a kind of silly thing to do, but we have to do it. And it follows because the real numbers are closed, of course, but our proof system does know that actually on line 4 here, but we have to specifically say it. In the future, it would be nice to be able to just say, I want to prove that c plus d is an r, and the system will look through the assumptions that we have and then see if there's a substitution that will work. But for now we don't have that, so I'm just going to manually do it. And having the choice to manually do stuff is always a nice thing. Let's do it. So what I want to do here is I want to use derive, and derive allows us to write a line in the proof. And the way we want to derive is with one of the rules. And one of the rules we have is the generalized for all. And so that allows us to do a for all and instantiate all of the for alls with a value at once. Before, there was just the regular for all rule, which would only uncurry one layer at a time, so we're not going to use that right now. We're going to use the better one. And specifically, we're going to use it on line 4 with c and d. And you'll notice that I'm talking about lines via their proof line index, which is a quick way to talk about things. So when we do that, I guess I might have messed up something, so let me try that again. Derive generalized for all using line 4 with lines 2 and 3, and yeah, it looks like I just made a typo. We get c plus d in r as we needed, so we have that, and now we're going to use it with this rule, and for x and y we're going to replace it with a and b. So what we're going to do is we're going to do derive generalized for all using 6, where k is going to be c plus d, so that's line 7. So membership in R is what we need to unwrap a layer of a for all that says k in R, so we're going to use 7 there. And for x we're going to use that a is in R, and then for y we're going to use that b is R. So then we do that, we get this fact. We get that a plus b times c plus d is equal to a times c plus d plus b times c plus d. And that's just one layer of the expansion. We need to then unwrap this layer. So we're going to use the previous rule actually. So we're going to use derive generalized for all, and we're going to use it on 5. And here we want k to be a, so we're going to use 0 for k. And then what do I want for that? I want c and d, so I want 2 and 3. And what we get here is the expansion of this. And we just want the same thing, but instead of a, we want b. So we're going to use derive generalized for all 5, 1, 2, 3, and we get that. And this is good. Now, what we want to do is we want to change this goal. So most proof systems have this where you can either generate lines of the proof, or you can change what your active goal is by rewriting it or using things on it. So, for example, we know that a plus b times c plus d is equal to this whole thing. So let's try rewriting the goal with that in mind. So we're going to do goal, rewrite, and then we're using the left-hand side. We're replacing instances of the left-hand side of this equality with the right-hand side in a target into the goal. So we do goal rewrite using the left-hand side of 8, which is this line, which is the equality. And what we get here, you'll notice at the top, is that it expanded out to this. And then we can quickly kind of do that same thing with 9 and 10. So we're going to do goal rewrite LHS 9, goal rewrite LHS 10. And you can see that we just expanded this out to be the same thing. So we have this thing equals this thing. So that's clearly true. And when we have x equals x for any term x, we can say goal EQ, and the proof is done. So of course this could be streamlined, and as the system gets used more, the system becomes more streamlined because more, you start wanting to make your experience better. So that'll happen, but I just want to demo it in its current state and show that we have a working thing here, which is great. And yeah, that's it.